Hello and good evening everybody. So we were discussing in this class about the different halogen compounds and how they are useful for industrial purposes. So after fluorine we were now with bromine. So the elemental bromine production we have seen that how this can be utilized for different purposes. Now today we will just go for its other compounds such as your hydrogen bromide. So HBr we all know is a very useful compound like that of our HF and HCl, and HCl as the typical mineral acid is largely used in different sectors of the industry, but HBr is not that much useful as an acid, but it can be useful as a brominating agent sometime. So when we consider that how we get HBr from elemental bromine also, so from the natural sources we have seen that the seawater was useful to give you the bromine, and that particular bromine if it is in your hand we can convert it nicely to HBr. So the direct combination, this manufacturing process or the process utilized for the industrial scale production of HBr is dependent on the combination of bromine and hydrogen, that means Br2 and H2. So that combination in a straight way can give you two molecules of HBr. So those HBr we can handle and those HBr can be utilized for different purposes. So as this HBr what we have in the form that what we get this HBr, that HBr dissolves in water forming HBr acid. So HBr when it is dissolving in water we get it as like your HCl. HCl we know that the gaseous thing HCl which is being solubilized in water giving you the hydrochloric acid in aqueous medium. Similarly this particular one is also soluble in water. So at 25 degrees centigrade HBr dissolves to certain extent which is 193 gram and which is dissolving at 100 gram of water. So in all these cases whatever amount of this, that means we can have the H2 plus Br2. Br2 was a liquid, red liquid in your hand and direct combustion. So you must have a combustion chamber. In that combustion chamber we produce HBr, and the produced HBr we have to take away, and by dissolution in water you can get the corresponding aqueous solution of HBr for the different purposes. So along with this HBr, if we consider what are the different other bromates, so it's not that suddenly we are jumping from some alkali bromates, but it has some relationship because we have seen earlier that these two things, that means the bromine can disproportionate between the two oxidation states of Br center. It is Br minus and BrO3 minus. So the bromate one which is the oxidizing agent and its alkali salts, that means the corresponding sodium salt or the potassium salt or sometimes the ammonium salt are very useful for industrial purposes. So these bromates if we get, how we are getting these particular bromates? So again it is manufactured from the starting material of Br2, that means the bromine we can have like that of our HBr formation. So HBr formation you have, and that HBr when react with some amount of bases, that means sodium hydroxide, potassium hydroxide or lithium hydroxide, give you corresponding alkali bromide salts. Similarly, if we are able to make the bromate salt which is BrO3 minus, the typical anionic part of these bromate salts are BrO3 minus. So these BrO3 minus are electrochemically produced, that means the electrochemical oxidation of bromine as Br2, bromine oxidation state is 0. So that elemental bromine can be oxidized electrochemically to get the corresponding bromates. So in a typical fashion what we see that the reaction of these in an electrochemical fashion, that means sodium bromide, we get it from HBr, HBr on reaction with other thing, that means starting from your sodium hydroxide to sodium bicarbonate to sodium carbonate, it gives you the sodium bromide as the typical salts. So, the alkali bromide salt, when it is dissolved in water, again like that of your HBr, is highly soluble in water, and that aqueous solution we just try to go for electrolysis. So, the electrolysis of this particular one, and what we see that the entire amount of bromine as Br minus, so the bromide ion. So, bromide ion can be converted to NaBrO3, that means this particular one is a very neat one, that means electrochemical oxidation is very feasible for the oxidation of the bromide ion to give you Br minus to BrO3 minus, and at the same time we always know that some component, if we try to oxidize it, we get the other component as the reduced form. So, from the water medium, if we have the protons, that means H plus available, so those H plus will take up those electrons during oxidation of the bromine, will be reduced to the hydrogen. So, hydrogen gas is again a byproduct for this particular reaction. So, from this reaction, if we consider that no, we have simply the bromine, that Br2, and if we want to get that particular Br2, from Br2 that sodium bromide as well as sodium bromate, what we consider that one is the reduced form, NaBr is the reduced form from the bromine center or the bromine or the elemental bromine. Similarly, the bromate, the BrO3 minus is the oxidized form. So, if we allow some amount of disproportionation reaction between sodium, between this bromine center, so one of the bromine center can be reduced to Br minus and another can be oxidized to bromate center. This was the original principle what people considered earlier, that if we have both the availability of bromide salt as well as the bromate salt in sulfuric acid medium, if you go for H2SO4 medium, these two can combine together to give you the production of elemental bromine. So, that is the another way of getting your bromine, that means the preparation of the bromine, what we have seen through oxidation of the seawater by chlorine. So, if these two are plenty in availability, that means if both bromide as well as the bromate salts are available in nature or some other industrial sources, we can combine them together in sulfuric acid medium to production of your bromine. So, the disproportionation reaction in that way, that means the electron transfer reaction is very much feasible for this bromine, elemental bromine, for giving you this particular bromate salt, and when we use this for your direct combination of hydrogen, we get the HBr and its corresponding alkali bromide salt. So, after getting this particular bromate salt, what we use that alternatively it can be manufactured also by passing simply the chemical reaction, utilization of the chemical reaction, that means the elemental bromine Br2 in alkaline hydroxide solution. So, alkali hydroxide solutions like that of your sodium hydroxide or potassium hydroxide again allow you for getting a disproportionation reaction. So, that particular disproportionation reaction from Br2 0 giving you Br minus as well as BrO3 minus. So, you get a mixture of bromate as well as the bromide, from which how we separate it out, your bromate salt is less soluble, that means it is poorly soluble. So, it will be separated first, then we get the sodium bromide. So, sodium bromide will be highly soluble, so it will remain in the solution when most of the bromate or the entire bromate can be separated as sodium bromate. But remember it, both of them are the corresponding sodium salt, but depending upon the anionic part, one is the Br minus and another is the BrO3 minus, the bromide bromate thing. So, they can basically separate it differentially. So, you must have a typical combination of these two. So, if we allow in alkaline medium only, so if you have this typical alkaline medium, that alkaline medium can go for this particular disproportionation reaction, and if we try to get the reverse one, that means the combination of bromide and bromate mixture to produce the elemental bromine, we have to go for an acidic medium. That means in that particular case, the H2SO4 medium is sufficient to combine bromide and bromate to produce Br2, and the alkaline medium is sufficient to give you the corresponding disproportionation between the bromide and the bromide mixture. So, whatever raw materials is in your hand, judicially you have to think of the corresponding procedure and your demand for all these elemental things, that means the bromine as well as the bromine compounds, and we are not taking much more examples, we are concentrating our attention on Br2, and two of these bromide compounds, the bromide compounds or the bromate compounds is the NaBr and NaBrO3. So, what are those applications where we can use this particular one, that means where we can use these compounds. So, one of the industrially important compound is the additives what we use in the fuel. As we all know that the tetraethyl lead was earlier we used as the anti-knocking reagent to increase the performance of the fuel while it is burning in the internal combustion engines. So, another organic compound which is the dibromo derivative, basically 1,2-dibromomethane. We know that if you have the corresponding methane is CH4, so two of the hydrogen atoms from the methane center can be replaced by the bigger bromine centers, we will get it is dibromomethane. So, that particular one is utilized for your leaded petrol as lead substitute. So, it is a particular fuel additives when the lead can be removed through the formation of lead bromide. So, lead was present as tetraethyl lead. So, tetraethyl lead can react with your the dibromomethane to produce your lead bromide itself and the corresponding methane which can be burnt inside the corresponding fuel. Then we can see that the some of the important brominated compound as the fire reducing agents or fire retardants. So, what are those compounds? Because the substitution of these things on the entire organic molecule can give you something that where the fire is there and fire is trying to burn all the available material around. That means, if you have only the hydrocarbon part, that means any fuel or simple methane or ethane or any other hydrocarbon, it will burn very quickly such that you can have the corresponding burning for destruction of your CH bonds or CC bonds, giving you the production of the corresponding water molecules from the hydrogen of the hydrocarbons and the carbon monoxide initially and finally carbon dioxide for the production of all the carbon oxides. But if you use some brominated diphenyl ether, what is that? Is a very simple, you have the diphenyl ether, we all know ethers are ROR. When you have two of the phenyl rings attached, that means PHOPH is the diphenyl ether. So, is a bulky one and which should not be very fire friendly, that means it is not very easy to burn it very quickly. So, the brominated form of these, that means it is further brominated also, and this particular compound it has a huge industrial demand also as a fire retardant agent. Currently account the largest number of bromine chemicals what industry produce for us. Okay. So, why this particular one is very useful is that the ease with which the CR bond can be broken, which basically produce the organobromide compounds, which are very useful material as the flame retardant. So, if you break the CBr bond of the diphenyl ethers which is brominated, so the intermediate compound what we get basically after the removal of the bromine, so that organobromine compound basically can destroy the supply of the corresponding fuel and can reduce the corresponding flame or the fire. Another example of these phenol based compounds, because these are all very much important and industrially those are very important and they are basically value added compound in terms of the bromine addition to the organic molecule or the organic chemicals. One such is further bromination is the tetrabromo bisphenol A. This is a typical variety of that. So, is a bisphenol compound, and that bisphenol compound we all know that what is phenol, and you can have two of these a bisphenol compound, and which is basically substituted in 4 different positions for your bromine incorporation. So, It is basically coupled together with this particular center, where is the carbon center you have, that means it is not CH2, but dimethyl C. So, dimethyl carbon is there. So, it is 2 methyl function as the carbon. So, dimethyl carbon attach phenol unit from the para positions, and further it is substituted for its 4 positions of CH, 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 CH by CBr, 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 CBr. So, this compound is mainly used for as a reactive component or the starting material or the component for polymer formation. So, it is a reactive component of polymers by incorporating into the polymer backbone. So, bisphenol polymer we know, and if we try to improve the property of that particular polymer, we incorporate a proportionate of this bromine derivative of bisphenol. So, this bromine derivative of bisphenol along with the original one, which is not bromine derivative of bisphenol compound, through polymerization give you a variety of a new type of polymeric compound. So, the lower grade of this TBPA, so this TBPA which is not highly pure basically, but the cost of production of that particular TBPA is less, which can be very useful in preparing the epoxy resins. So, it is not a simple type of polymer, but making of epoxy resin is useful, and in the electronics industry it is basically used in the PCBs, the printed circuit boards. So, you see we know how, because it is basically in the domain of polymer industry, but we are not talking all these things, but it is utilization, how you use the brominated compounds, because we are talking in terms of the consumption of bromine, the production of bromine and the bromine derivative of this thing. So, if you have elemental bromine and you know the procedure how your methane can be brominated, only the techniques you should know, how methane can be brominated, how your bisphenol can be brominated or bisphenol can be brominated. So, the bromination technique will give you the starting material where the bromine can be consumed to a large extent for making these new compounds for very useful industrially important materials. So, but is controversial because these are persistent pollutants. So, not only your bisphenol compound or the bisphenol A compound, because we always try to restrict our use of this polymeric compound, because it will not be destroyed in the environment, it will remain in the environment for many years. So, the brominated variety is also, because once the compound or the polymer is available, we throw away the compound after use or after rejection. It is the burden of the environment. So, basically it is a controversy, but if we take a proper precaution, bromine can also be utilized very nicely for making all these useful compounds. Then they are also useful in another area which are known as your fumigants or biocides. Biocides, we know that how you destroy the biologically available different dangerous things, that means the corresponding one, the herbs which we do not require. For that purpose we have to make through bromine ethylene bromide, and that ethylene bromide obtained by the addition of simple bromine addition to your ethylene molecule. So, the direct addition, so is the typical addition reaction of bromine through on the carbon-carbon double bond. So, is also a commercially important procedure as a component of leaded gasoline. So, ethylene bromide again like that of your dibromomethane, we add it as the corresponding leaded gasoline component for your improvement. It was also a popular fumigant as agriculture. So, not only your addition to the gasoline material, but ethylene bromide is also a fumigant in agriculture, because in agriculture we sometimes spray all these things displacing the original one. Original one is 1,3-dibromo-3-chloropropane. So, it has a overburden of not only 2 bromine centers, is a dibromo plus 3-chloropropane molecule. So, is less harmful compared to this compound DBCB, that we use simple ethylene bromide which is only bromine based. Then we can move to making some dyes. Dyes we all know that which is a very useful color absorbing material, and dyeing industry span from textile to your paper industry to cloth industry, and everywhere we can have the dyes. So, the dyes which are nothing but your brominated dyes. So, indigo, we know that indigo earlier it was naturally produced, we produce indigo from agricultural sector, but during this particular knowledge that we make this indigo dye in the laboratory. So, that is useful, we know, for our textile industry, that blue color of the indigo we put on the jeans material. Then to improve that material for its life or for its utilization for its industrial processing, which is useful for your textile material, we can go for its bromination. So, what we should know? We should know a little bit that what is indigo and how indigo can be brominated, and that indigo bromination can improve the quality of that particular dye. So, that particular step we are only considering or focusing our attention, that how the bromine industry can help in making this 6,6' dibromo indigo molecule for a useful dye molecule. So, this particular one, so we have these two selective positions, and is most of the time it is like that of your bromination of the ethylene. Is a direct one, we take indigo and we go for its typical bromination, that means sometimes we simply add bromine. So, that particular thing can so good, that means the reaction is so facile that immediately the bromination can take place through the direct aromatic substitution reaction, because you have the two phenyl rings and we have the phenyl CH bond over here and another phenyl CH bond is here. So, you get the corresponding aromatic substitutions, aromatic nucleophilic substitutions by the bromine centers to give you the corresponding bromine derivative. The way we get for a simple organic molecule, such as that we know that for analytical reagents we have the oxine molecule, that 8-hydroxyquinoline, and if we want to derivatize that as the corresponding bromine derivative, it is simply through addition of elemental bromine, drop by drop diluted solution of bromine addition to that particular organic molecule, or sometime in situ, that means within the reaction medium we produce bromine. So, production of that bromine, again we know, just now we have seen that the combination of bromide bromate mixture can give you the liberation of bromine in a particular acidic medium. So, the acidic medium, the slow release of that bromine through the production, and then again the organic molecule, if it is available, will attack that organic molecule and produce its brominated version. Similarly, some procedure we should have also for industrial or large scale production of this dibromo indigo molecule. So, this is also another important application of your bromine compound, and lastly we will see that how the pharmaceutical industry can also be benefited, because the pharmaceutical molecules we all know that can be used as a useful drug molecule or is a useful medicine for our purposes, for our use. So, those molecules we know that is there, sometimes they are very big molecule, they are mostly the organic molecules, sometimes they are heterocyclic structure, having a heterocyclic structure, but new drug discovery or new drug molecule availability sometimes is dependent on a very simple reaction. It is nothing but a simple bromination reaction. Earlier we have seen that a particular type of molecule, organic molecule, which is a pharmaceutical molecule, that pharmaceutical industry can take the advantage of typical fluorination. Now we will see that the typical bromination can also change the corresponding structure. So, do not worry about the complicated molecule what you have in your hand, but it is the molecule what you see, that this particular molecule, the entire part we know, you have to know. Just now what we have seen, that the dye molecule can be brominated. So, similar type of bromination can be achieved on the pharmaceutical molecule, where we see that this particular CBr bond. So, without that CBr bond, the function of this is again there, so that the whole molecule is also a functionally active molecule, and which is nothing but a niceragolin, so which is a vasodilator type. This function is a vasodilating activity. So, is a vasodilator niceragolin. So, vasodilator niceragolin can be formed when you get a typical brominated derivative of the original organic compound. So, what we have, the whole molecule you can consider as R, and you have this CH bond as RH, like that of your methane or anything else. So, which can be brominated to give you the corresponding big R molecule as the pharmaceutical molecule, as well as the corresponding insertion of the bromine at a specific position. So, bromination at this particular point, at this particular position, can tell us that we can improve. Sometimes it is not always true that we can improve the quality of the pharmaceutical through bromination. So, if we are able to improve the quality or its performance in terms of its activity, we can go for its bromination. So, one more example also we can have this, and again it is a little bit complicated molecule, but forget about the complication in terms of its pharmaceutical structure or the pharmaceutical molecule. We are only focusing our attention for your brominating part. Again, if we consider that the whole molecule is your R and R is attached to your H, so H is there, so RH can be converted to convert that compound to RBr, which is again a drug responsible for sedation, so it is a sedative. Sedative brotijolam, and that sedative molecule is again obtained through bromination of the corresponding part, which is the corresponding thiophene ring. It is the heterocyclic ring. So, the thiophene ring here, you have the pyridine ring at one end. So, at one end the pyridine ring at the meta position is getting brominated. Here also the thiophene ring, the ortho position of the sulfur of the thiophene ring is getting brominated to improve the nature of that particular pharmaceutical molecule. So, this also can give you some other example that where the bromine can be useful for. So, tear gases are also useful. We will see, we will continue for our next class also. The tear gases, what are the molecule we use for the tear gases? So, it should be pungent, it's pungently smelling also, it can bring tears in your eyes. So, people discovered this molecule that the very simple molecule which are of only simply bromo derivative, is not the bromoform, it is not the other bromo derivative of any other small compound, but we know that acetophenone molecule has not such effect or only acetone. So, if we have in our hand the only acetophenone molecule and acetone molecule, and if we are able to brominate them through the use of the elemental bromine, we get the typical application of there as the tear gases. So, this is nothing but your tear gas smoke, and that tear gas smoke is basically available. So, this is the cell. When you break the cell, it is basically the fumes that people will simply move away from there to avoid that particular fumes. Then it is also useful for some inhalation anesthetics, which is 2-bromo-2-chloro-1,1,1 trifluoroethane. So, is one basically, it is 1,1,1 trifluoroethane. So, fluorine is there, chlorine is there, and bromine is there. So, it is a little bit complicated molecule, and that molecule is therefore is a very important, because what we see that in this particular case, once you have and the halogens, because we are talking after fluorine the corresponding use of your bromination. So, you have fluorination, you have chlorination, and you have further at the end if possible the bromination. So, this complicated molecule, it is again possible to make, and through inhalation anesthetic molecule. So, this anesthetic molecule again is possible to make through the introduction of your compound as its corresponding bromine derivative. Next, the next class will continue basically for the third the molecules. That means the elemental thing, the third elemental thing is your iodine and iodine compounds. So, when we talk in terms of the iodine and iodine compounds, the iodine compounds are completely different if we have some little bit of experience of knowing that what iodine compound is. So, we have the fluorine as the corresponding gas molecule, then bromine as the liquid, but iodine in its room temperature laboratory condition, it is present in the solid form. So, it is sometimes very easy to make it, that particular iodine molecule, easy to store it, and sometimes we will find is also a very useful reaction in terms of its reactivity with the different materials. So, the sector, industrial sector which is producing large amount of iodine can make more and more new compounds which are also very much useful industrially. Thank you very much.